I'm going to talk about this project. This is hopefully going to be a more thorough version of what I talked about at SC 24 because I think I had like 20 minutes there and it was a little bit tight. So I'll tell you about this project, which is predates me, and I'll explain the history and the contributors and how we've used it. So I started working on this project when I was at Intel, and I was there for almost 7 years, and we did a lot of interesting co-design things. Lots of software co-design, which is easy to talk about. We did do some hardware stuff, which I can sort of talk about, but I'll explain the uses of this code. I'm fairly proud of this. Tim Mattson retired, so I'm the curator and maintainer and developer at this point. But I think there's some lot of neat stuff in here, and I think it's a really useful tool for computer scientists. I think it's at this point somewhat unique, and I'll talk about the landscape for that. Yeah, so Tim Mattson created this sometime starting in the 1990s, and Tim was motivated to understand computer architecture, and of course, in the 1990s, parallel computing wasn't exactly the thing it is today. Nowadays, everything is SIMD, everything is multi-core. But back in the day, things were a little bit simpler, and so some of the kernels were really a sequential thing. There's a branch prediction kernel, which, I think there are some interesting generalizations of that, but that just shows you sort of how the scope was trying to understand architecture very generally. And then a couple years before I got to Intel, Rob van der Wijngaart, who's now my NVIDIA colleague, worked on developing the initial parallel implementations with MPI and OpenMP as they existed in the good old days, CPU only simple stuff. But focused on implementing the algorithms and designing the parallel scheme, which is something I built upon. And so when I joined, we were interested in exascale and programming models in general. And so we did a lot of study, which then spawned some new ideas. And then I sort of did some things I'll talk about. So a lot of people have contributed. Obviously, a bunch of people from Intel contributed because we try very hard to be lazy. One of the things we're trying to do with this project is have it be a fair study from the standpoint of expertise, which means, Tim knows a lot about OpenMP, I know a lot about MPI, and if we wrote MPI and OpenMP, and then we also wrote all the code in UPC or Charm++, then that'd be a unfair comparison. So we enlisted a lot of these folks like Jacob Nelson at the University of Washington and others to help us. Or we wrote code and then we sent it to folks and said, tell us what we did wrong. And I've been really fortunate. There's some folks I don't know if Karsten Bauer is on the call or if he graduated but I believe he contributed some really good Rust stuff. If I have that, Rust or Julia, I'm sorry, I can't remember all the stuff now, but some really good stuff. And there's been a lot of contributions lately that especially on Rust and Julia that we could have done. So thanks everybody who contributed, and this should tell you, we are a pretty open project. If you're interested in playing around, it's both easy to contribute and we make it easy for people who are interested. So I can't tell you in any finite period of time everything that's in there. The goal is to make the code a useful resource by itself. It's not perfect, but I try very hard to make it curated well enough and documented well enough within reason. And you can find a lot of the stuff on GitHub. I'll reference things, and then if you're curious, the best thing to do is look it up. So I told you a little bit about the history. We started in 2014 with the hypothesis of MPI and OpenMP, are they good enough for exascale, right? So there were people, particularly some people at Intel, who said, no, OpenMP and MPI are dead. We got to go to all the new fancy new stuff, dynamic runtime systems. And Tim and Rob and I are pretty old fashioned, and we were like, no, we just don't think that that's true. So we're going to try to prove it. So what we did though is we embraced the challenge and we said, okay, well we'll go find some different models. So we looked at UPC, which is of course one of the classic PGAS models. We also looked at SHMEM. We looked at Charm++ and Grappa, both of which were relatively usable, mature C++ dynamic runtime systems. And we were looking at these because we could compare them to MPI and OpenMP, which is all written in C. However, what we learned in the course of this is, you don't actually learn as much as you should if you're basing all of your experiments on a C89 code base. So that this inspired me to go off and write a bunch of stuff in C++, because at the very least, I wanted to be able to say, well, if I ask some C++ people for help, I should give them a C++ reference rather than some C89 code that they don't like. And the other thing that happened is Brad Chamberlain, who's a really neat thinker in this space, was talking a lot about programming models in Chapel. And Brad talks about Chapel, but he also talks about very important general concepts. And one of the things that came out of listening to Brad and discussing some of this stuff with him was the idea that you can't always think about a single reference implementation in a piece of code as the basis for starting a new experiment. In Chapel, there's this notion of elegant code and optimized code, and they look different. And we know this shows up in a lot of, it sort of shows up in C++ and Python especially. There's not really any version of C that's particularly elegant, but that's because C's kind of, low level by design. But there became a point where I said, okay, I need to develop some sort of a different levels of abstraction and different levels of semantic expression in this, so we can compare that stuff. And so I went off and started writing other languages. And then I said, do we really want to compare Chapel to C89? No, we want to compare Chapel to Python, or maybe to Fortran 2008. So we started writing those things, or I started writing them in my free time. And then, exascale was pretty obviously going to be heterogeneous. Some folks might know the history. It took a little while for Intel to come around on that, because there was all Xeon Phi for a while there, and then everybody got on the GPU train. And so we started looking at GPU programming models. I had switched to the HPC business unit, and actually we used the PRKs for some of the original studies on oneAPI, which some of you have heard about, and Tim and I were part of that. And so we used it in that context. We looked at it from the standpoint of, are we going to be able to solve basic, interesting HPC problems with oneAPI? And we said, well, can we write the PRKs? If we can't write the parallel research kernels in oneAPI as it exists, well, then maybe we have a problem. And we did some other stuff. And, over the last 5 or so years, I have been doing GPU stuff. I haven't done as much as I would like, although I've picked up again more recently, because I was telling Georg, I'm switching from the HPC compiler product org to the Nickel NV team. So I'm going to be writing a bunch of Nickel and NV stuff in the PRKs soon, so I could teach myself. So that's the history of the project. This is the scope of what we've looked at, the intellectual foundation of what we're trying to accomplish. And we're not the first to do this, right? One of the things you'll see in the PRKs, if you know history, is there's a lot of similarity with the NAS parallel benchmarks in the HPC challenge. And that's intentional. A lot of this stuff was derived from that. But one of the things that we wanted to do, or Rob and Tim wanted to do before I got there, was distill out something even simpler. Because as simple as the NAS and HPCC are, they're still hard to port. And this is something that's really, really important. When you want to do co-design, if you have to spend 3 months and get a domain expert to write a mini app, or to port a mini app, or to port some sort of benchmark, you've lost 3 months where you're not doing co-design. All you're doing is porting. And so we wanted to come up with something that had the same algorithmic bottlenecks, and yet was simple enough that you could port in about a day, which is about what I find the PRKs to be, sometimes a small fraction of a day, depending on the model. The other thing is you can look at some of these things. If you go look at a paper on the NAS parallel benchmarks, and then you go try to find the code, good luck. And that's this is a bit unfair comparison, because graduate students graduate, and SVN repos die and things like this. There's stuff that doesn't get curated forever, but we've tried very hard to make GitHub the living archive of what we do, rather than write papers about it and then throw the code away. So that if you want to go back and analyze something a different way, it's trivial to do so. And so we look at different aspects of the programming models. Some of them are more hardware centric, like bandwidth or latency, and then other parts are more semantic. Do you overlap something or not? And then there's also then the productivity. And so Tim and I care a great deal about programmer productivity, but we've concluded we have no way to measure it. And I'm pretty confident there is no real measure, and there's no measure of elegance. These are all personal properties of a programmer. But the good news is you can use the PRKs, and you can use that as a tool to answer the question for yourself, and then feel good about your answer, because you can go look at some things. So anyways, this is what we're trying to do. And then, of course, the biggest thing is you want to be able to measure things. So this is some statement of business or economics, but the fact is you can't do co-design unless you have an objective function. And so the goal of PRKs is to have a clear objective function when what Rob always said, you get a performance result if and only if you get the correct answer on it. There's no way to get a number out unless you've correctly computed what you said you were computing. And then Rob did a whole bunch of stuff to make it impossible to cheat because he found, I don't know if is anybody ever intentionally cheated, but there'd be cases where, you make a subtle error in a program and you get the right answer anyways. And then you realize that there's a bug and you say, well, this is weird. I wrote bad code, but I get an answer. And so you say, okay, how do I prevent this from ever happening again? So we've got all these numerical games in the PRK to make it so that you actually have to get the right answer. And the only exception to this is I did some stuff that was I have something where if you get a NaN, the if check is returns the wrong version of true and false with a NaN, and I had to clean that up. I don't think I've done it perfectly. So if you have to throw NaN exceptions if you want to be absolutely sure. But other than that, we're pretty robust. All right. So the parallel research kernels, they're designed to be universal, cover some sort of broad performance pattern across HPC that we care about. They have to be super simple. They have to be able that you don't have to know anything about engineering or physics or chemistry or whatever it is to port them or to understand them. They should be as easy to express in code as they are in math. Of course, depending on the programming language, they have to be fully portable. Obviously, exceptions for the fact that, CUDA isn't portable, but there's a portable version of everything, and then there's non-portable extensions on that. Extensible. So we have run the PRKs in cycle accurate chip simulators, and we've run them on machines with thousands of nodes. So this is one thing that's really, really useful. There were times at Intel where we actually had architects who were like, okay, I need to run something in a chip simulator. Do you have anything? And we could always point to the PRKs. We always had a way to make the PRK fit into what people could do with KIPs, 1,000 instructions per second or less. And then we did occasionally have to tweak stuff because some of the chip simulators will actually know how many bits you flip in a number. So we had to occasionally break things to make the chip simulators happy to put in the right number of bit flips or whatever. But we've done that. So we know, that's the sort of co-design you do. These actually work in this context. And then of course, verifiable, which I already mentioned. So now here are the algorithms. So there's, I guess there's 11. I think there's 11 different algorithms. I only focus on about 5 or 6 of them. Some of them are more interesting than others. So one of them is basically the stream benchmark with one tweak. So we accumulate, and we do this, one, because of validation, and two, some of you, if you've ever studied stream, know you get some really weird behavior on whether or not you get a non-temporal store or the ARM equivalent of that. So, if you're on x86 and you use GCC, your bandwidth number is different than if you use Intel. Same thing with AMD and AOCL, whatever. And this is because if you don't load A and you have, RFO versus non-temporal in x86, and so you do an extra load just to write. And so we eliminated that problem. It actually smooths out the numbers really nicely. And I actually contributed this into BabelStream because it made it nicer there. It cleans up the the A64FX number a lot too. We also have Stencil. So our Stencil is super simple compared to all the other stencils out there. It's sort of the torturous limit of if you do domain decomposition in 3D, you get something that's almost 2D, but it's not perfect. And if you want to use it for anything serious, you should tune it better than I have. But it works, and it gives you a reasonable approximation to a naive stencil. Matrix transpose is there. Matrix transpose primarily hits the TLB. So the most obvious optimization, which is built into most of the implementations, is TLB blocking, and then you can do some finer blocking, but TLB is usually the bottleneck in transpose. Point-to-point synchronization is the one that has the most variations because point-to-point synchronization does not map unambiguously onto any sort of computer architecture model. So if you have a network then it maps onto a network primitive. If you're in shared memory, it maps onto either atomics or other things, and I'll talk about it. So there's a lot of flexibility there in the implementation. And at one point, we were looking at some data flow stuff, and we used this kernel to analyze, well, what are the merits of data flow for this sort of a pattern. There's some other stuff, but I'll focus on these. The other one is if you really want to heat your office, which I do sometimes in Helsinki. I heat my office with my 4090. Is I have a whole bunch of matrix multiplication implementations, so I can fire up SGEM when because it's easier to do that with SSH than reach the space heater. So we wrote a paper about this for ISC. I guess it's 9 years old at this point, but it's a pretty good paper for the distributed memory stuff. So I'll just highlight the interesting parts, and then if you want to check it out, you can. So this is point to point. So I'm not going to describe all of it in detail, but this is basically strip decomposition. And what happens is process 0 starts, and as soon as it gets the block size, it sends a message to the next, and then the next one starts. And so you basically get a wavefront of all the processes going like this, and then they reach the end, and then they start over. So it's all latency sensitive, and you send a point-to-point message as soon as you get there. And so basically you will accumulate latency across. So if your message latency goes up by a factor of 10, you will almost certainly see some significant slowdown because of the last arrival taking a while. And as of course, strong scaling makes the problem worse. So you look at this, we've got a whole bunch of different models. The thing that's relatively obvious in here is that if you're going to do something that's point-to-point synchronization, MPI point-to-point does a pretty good job. Send receive does what you'd expect. MPI shared memory for the node part of that with atomics is even better because, of course, 50 nanoseconds versus 500 nanoseconds, give or take, for shared memory. You see, SHMEM does really well. This is a Cray machine. You kind of expect that. The Cray SHMEM implementation, if I recall, does better than any others. In this case, same thing with UPC. Cray UPC was better in most cases, but maybe not here then. Anyways, there's some variation in the implementation quality of SHMEM, which sort of comes out here. And you see, not surprisingly, Charm and Grappa don't do so well. And the reason is they're actually both designed to aggregate fine-grained synchronization. So this is actually the worst sort of torture test for them, because they're trying to say, well, give me a whole bunch of fine-grained operations and I'll bundle them up and make them go faster than they would if you had direct injected them. And we're giving them one at a time. But it was useful to do the study. And what you can see actually is Grappa isn't so bad at smaller scales where some of those latency hiding properties actually can come out. Transpose is we're doing a one-dimensional decomposition, and the reason we do this is we're not trying to mimic the matrix transpose operation you might have in some sort of a tensor contraction or quantum chemistry. We're actually trying to model the NAS Fourier transform thing, which if you look at NAS Fourier transform, it basically bottlenecks in this all-to-all transpose rather than the local compute. That's not too surprising. Local compute is fast relative to networks most of the time. And so we just basically cooked down the NAS FT until it was something which does transpose with send receive most of the time. And what you see here is a very reasonable behavior based upon the property of networks, which is SHMEM, which is doing our direct RDMA with no overhead, no protocol stuff, does the best up to a point. And this crossover point is, you can see down here, 50 and 36 cores or endpoints, is, if you're doing a flat programming model, is 8 kilobytes per endpoint. And if you go to a hybrid model where you do the node and block at the node level rather than the core level, it's quadratic decomposition. So you get 4.5 megabytes. And so down to about 8 kilobytes, in the message size, the network performance is basically flat. Once you get below 8 kilobytes, you switch over from being, bandwidth limited to being latency limited, and all the protocol overheads come into play. And so what happens when you get out to 12,288 is you're now down to 2 cache lines per endpoint if you don't decompose hierarchically, and you're at 72 kilobytes if you do. And so this makes a huge difference. And this is obvious, right? I mean, but in 2015 when we were doing this, it was useful enough to be able to say, well, this is what's going to happen when we start strong scaling if we build a machine with 1 million cores, et cetera, et cetera. And so you can see some subtle variations between the models, but the basic idea here is everything you'd expect out of standard network analysis of essentially once you get below about 1 page of memory, your message performance starts to become not data bandwidth limited. It becomes limited by all the other junk. So this all made sense. It's easy to understand in hindsight. This is a really good benchmark for a lot of purposes. If you want to show PGAS versus send receive, I've rewritten all this stuff. Actually, some of the stuff uses all now, but I haven't hopped onto a create or remeasure. So at the end of this, we wrote a report, an internal report, where we basically said, MPI fault tolerance is about the only problem we're going to have. OpenMP, as long as you do good hybrid programming, you should be fine. We don't need to throw all the code out and start over, but we're going to need to do a little bit more than C89 and OpenMP3. So we're going to have to look at GPUs. Then we're going to obviously have to see what C++ and other things can do, because nobody was writing C89 at that point. So I started this in my free time because it was fun, but I also sort of overlapped it with my day job, writing all the languages. So started with, I think, C++ and C11. So C11, I basically just rewrote Rob's code to use modern C syntax and cleaned up a bunch of things, but it was otherwise the same. And then wrote all the modern OpenMP and C11 threads. And then I did the same thing with C++. And one of the things I did there, I did TBB, I did the parallel STL, did Cocos and Raja. And then at some point I can't remember which year it was, I discovered this, then I did OpenCL and CUDA. And then I found this thing called Sickle. And I just found it because it was on slides where people talked about C++ for accelerators. And so I started writing Sickle. And then I think it was about 6 months later, somebody called me up and basically said, we're going to do this thing called One API, and we hear you've written Sickle before, and we're probably going to use Sickle. And no one else has ever written Sickle before, so tell us what you think. And so then I got involved in sort of the development of One API and data parallel C++ and Sickle, which thankfully basically became Sickle. And so there was a lot of things we learned along the way with software from that. I've also written all the Fortran. All this is modern Fortran, evaluating co-array Fortran, especially because of the PGAS connection. Also, if a lot of computer scientists hate Fortran, although that's more of an American thing than a European thing. Modern Fortran looks a lot like NumPy, and so one of the things I've tried to do is write Fortran that's as pretty as NumPy, and then you can trick people into thinking that they hate Fortran and love Python by showing them Fortran code that actually could be mistaken for Python. And so we've done a bunch of stuff. More recently we've done MPI for Pi and then Shmem for Pi, because I convinced Lissandro and his student Marcin to do Shmem for Pi. And so we can actually evaluate that stuff with this code because it was easy enough to port. There is some Chapel stuff. It took me a long time, but I merged it a couple months ago. So the Chapel stuff is in the repo. So you could do a whole lot of studies. And actually, there's a whole bunch more languages that you'll see at the end, all the non-HPC languages that I think is kind of interesting. So let me talk about some sort of, this is less hardware co-design, but more observing hardware properties. So this is Stencil. And this was a fun one because I wrote TBB and I didn't know what I was doing. So I just, looked the pattern and I said, okay, I'll write some TBB. And then I wrote OpenMP. And the TBB version won by like a factor of 2 on KNL. And I said, well, I'm sure the TBB team will be excited to hear about this, but this seems fake because, they should both hit the same bandwidth number. And it turns out, of course, TBB's pattern is this abstract, blocked C++ cool thing that you do the right thing automatically. And then, of course, OpenMP, for better or for worse, does exactly what you tell it to do. And so you tell it to write a loop that goes like this, and it'll do that loop. So it doesn't have any blocking in it. And we don't have any OpenMP compilers that do any of this stuff yet, although I guess OpenMP 6 might. And so you can actually compare this. And then, of course, at some point after this, I wrote the OpenMP blocked version, and the numbers got exactly what you'd expect. But you can see here a couple of effects. One is, OpenMP wins on the low end because it's got all the affinity business and lays everything out in a simple way, and that works well when you've got a small problem, whereas dynamic scheduling in TBB and OpenMP has an overhead and takes a while to pay off. TBB is much better at dynamic scheduling than OpenMP was, at least when we did this. Maybe the runtime's better. We also did Raja and Cocos, and the results are not interesting because you're seeing the OpenMP backend effect. So yeah, this is just fix all the things, write the blocked version, and now TBB is about even, although it's still a little bit different. I never figured out why it was asymptotically better, but I think it may have something to do with the KNL having a 2-tile per L2. Anyways, this is another one. This was a while back. I got access to A64FX at Georgia Tech, and I did the same experiments. And I found, KNL and A64FX, if you know the architectures, really should be kind of the same. They're both, very lean on cache and very high on bandwidth. And yet I looked at tiling, and I actually had the tiled version in C++, but not in C. And I saw these weird numbers. I said, well, why is C faster? That makes no sense. It turns out it was tiling, or the lack thereof. So in this case, for reasons that I did not understand, because A64FX wasn't that important to me, I don't know why, other than I do know that tiling was really bad. And I tried a whole bunch of tile sizes, and they were all bad. And so I concluded, either something weird about the architecture or the compiler that makes the tiled implementation unfortunate. And, obviously at this point, it's probably not worth going back and finding out. But it was certainly interesting to see this. And, I'm sure that somebody who writes stencils for a living has already solved this problem on Fujitsu's machine. But, this was something that the reason this is useful to me is if I step onto a machine, the first thing I do is run the PRKs, and then I learn all this stuff in about 2 hours. And then I know, okay, this is a weird machine because tiling doesn't improve the performance like I'd expect. And then I can go and approach whatever I'm going to design in an application with more information than I would have had if I just, looked at some vendor PowerPoint. All right, so now I'm going to talk about wavefronts. This one is fascinating to me. I used to hate this kernel because it wasn't, it didn't resemble quantum chemistry. And Rob and I would argue. And then after a while, I ported it enough times. I said, this is actually the most beautiful thing. And so what's going on here is you're basically doing this trailing update. So you can see it in the pattern, you can see it in the code, which is a slightly modified version of the C code with the array notation. But the idea is you have a loop carried dependency, and you absolutely cannot do any of the data parallel stuff you do in any of the kernels. And if this is basically dynamic programming simplified. It has a lot in common with deterministic neutron transport, which is important to certain government agencies because of, radiation transport. And then because of dynamic programming, it also gets used, something similar gets used in bioinformatics. So it's a useful kernel for as a proxy for those. That's a heck of a lot simpler than writing a genome sequencer. So the first thing you can do with this, if you want to get data parallelism, is you can reorient the iteration space. So you sort of, think about it like a deck of cards, you push it sideways and then everything lines up. So now you can have a sequential loop over the anti-diagonals, which I'll show a picture of in a second, and you get parallelism. This isn't actually good, really, but it's better than no parallelism in some architectures. So this is sort of the only thing I can do in OpenCL, for example, without violating OpenCL semantics. But this is the OpenMP SIMD version of that. Obviously, you can put any parallel loop you want on the inside of it. You do some arithmetic to change the indexing. Took me a while to do that. And basically, you just go down these anti-diagonals and do as much work as you can. This is actually going to be garbage with SIMD because you know that none of these are contiguous. And if you generate them with AVX 512, all you're going to do is go gather single FMA or 2 or 3 FMAs, whatever, and then gather, scatter. So you'll spend all of your time in the gather, scatter engine and not any time doing anything else. And you probably won't actually win much unless your architecture is really, really strange. But it's a useful test and it works in some cases. So then, and what you do is you think about, okay, how do I make this better? So the first thing you do with the anti-diagonals, and you could say, well, what if I unroll that? And I do a couple of anti-diagonals sequentially at a time. So I do fewer than order n barriers. And then the other thing you do is you go back to what the original code looks like and say, well, what if I don't tilt the iteration space? What if I actually do the data flow, but I do it at a coarse thing? So, your physicists, renormalization group. So you sort of make this supersites, and then you do the flow the same way. And so then that becomes a task dependency. So this became really interesting in a couple contexts because there's a bunch of different ways to implement these primitives. One of the things that we had some Intel folks who actually were writing the CUDA version, and they wrote a really fancy version with CUDA cooperative groups that I haven't managed to maintain. But this is an example of some of you can see some of the things with the newer hardware features like independent forward progress and group synchronization in the GPUs, which NVIDIA has, that lets you write different code that you can't write with a sort of the traditional OpenCL execution model. So if you write this with OpenMP tasks, it's really easy to write. I actually love the elegance of this, but you still have to block it. The compiler won't do any of this for you, so you write the blocking and then you do all the arithmetic, or where you don't have to do the hyperplane arithmetic. You just do the blocking arithmetic, and it works pretty well. And then you can do do across, which is also in OpenMP, and sort of, I guess, is better, but it's not actually better because nobody implements it in a way that's any different than tasking, from what I can tell. It's essentially, if you look here, you type a very small number of characters less, and you get the same implementation, from what I can tell. There's probably a way for fancy compiler people to do better, but nobody has such a compiler in production. Lastly, you can do the hyperplane with the blocked loop, and this was a real pain in the butt to do all the arithmetic on, but it works. And I cheated and made it square because I was lazy. So you could compare these, and this is on Skylake in a given year, many years ago, and things that will change. So what you can see is Duocross did badly, basically because I think nobody uses it, and therefore Intel didn't bother to optimize it. They did optimize tasks better. Tasks works pretty nicely. Hyperplane worked the best. One of the things that was really fun about this, and I don't have this code because it was proprietary, but at some point there was an Intel processor architect who was really interested in understanding barriers, and he took this workload, and we worked together, I think, with Jim County, and basically a processor architect did the equivalent of what you would do in an engineering lab with an oscilloscope. Basically wrote the most micro-architecturally aware barrier that you can possibly implement on a given Xeon, and got the barrier latency down to, I think it was around 1,000 clock cycles on a Skylake socket, which was really quite incredible. And then we plugged it into this, and I don't have the number because I don't show that number. But it was an example of finding a workload that was extremely barrier sensitive, and then having somebody do very, very low level co-design on how do we write a piece of code that will make this workload go faster, and then figure out, well, okay, is there an architectural bottleneck that we can overcome? And that, of course, is a really interesting thing, because modern multi-core chips have a lot of cores, a lot more even than 28. So these things start to matter. There's some stuff out there that I'll spare you the details. And then there's an NVIDIA talk where I did something similar with all the NVIDIA models, a simplified version of this. But I'm going to go on to the language study, which maybe is less co-designy and more just like what's true and not about programming language showdowns. I will say there's the computer language benchmark. I can't remember what CLB. Anyways, there's something where people do this, and it's a really nice, thorough study. But the problem is that the code that they write isn't HPC code. It's like, they'll do some like n-body simulation, but it's like a tiny number of particles, or it's not written in a way that resembles HPC code. And so there's not a lot of good ways out there to compare programming languages. And this shows up, and you'll see these people will write papers. Well, they'll say, oh, Python is more or less energy efficient than C. And you start looking at the numbers, and you'll see like, well, how is C like, twice as fast as Fortran, or vice versa? And you go, this is just nonsense. There's no way that a competent C and Fortran programmer don't converge to exactly the same runtime for an HPC kernel for everything that I know about. And so you see some of these silly studies, and they're clearly just based on code that isn't well written. So I try really hard to make this stuff useful. Sadly, nobody wants to go do their data center power aware programming language studies with it. But if they did, they'd probably get more useful information. So let's see. I can't remember the order exactly, but everything but Ada was written a long time ago. Java is easy to write. You just, pretend it's C++ and then fix all the syntax errors. And then you figure out that C# is basically just, Microsoft Java. And then, I went off, and I don't even know what I'm doing with things like Lua and Ruby. They don't even work like normal languages by my definition, because I don't know how to allocate heap arrays and things. But I wrote stream in them just to have it. Rust has gotten some serious study, because Rust is neat, and people who love Rust, really love to tell everyone how much they love Rust, and that's great. And they write all this cool code. And so there's some really neat stuff with Rust in there that you can check out with Rayon and other things. that demonstrates, I think, that Rust is really quite compelling, even though I'm not an expert. We have a lot of Python stuff. Obviously, part of it's because it's so super easy to write Python code, and therefore you can do all sorts of studies without doing much work. And then the other part is Python is, one of the most widely used languages in the world. Julia is a similar thing. We actually studied Julia because, Tim was involved in that effort for a while. And, I was really interested in, how well is Julia serious? How does it compare to Python? Let's get some objective data. And it turns out that, when you're doing something that's a wrapper around C code, like matrix multiplication or transpose, Julia and Python are the same, give or take. And if you do something that runs in the Python interpreter, but Julia compiles with LLVM, Julia is 1,000 times faster than Python. So, if you know what you're doing with Numba and Python, and NumPy and all these things, you'll do well. But if you don't know what you're doing and you just want to write simple code, Julia is really, really quite compelling. Again, I don't own any stock in Julia or Rust Inc. I just, spent enough time looking at them to say they've really done well in this. Java, ironically, does really well in the PRKs, although I'm not going to tell anybody in HPC that they need to use Java. Go did not do so well. You could blame me. I also did Ada. Ada is it's like Rust, but with the syntax of COBOL, if you can imagine that, or old Fortran maybe. It's really painful in that absolutely nothing you want to do or can do in C and C++ will compile with Ada when it comes to implicit casts and the like, same as Rust. So it makes it really, really hard. However, like Rust with Ada, when your code compiles, it runs correctly. It just takes you 10 times longer to get it to compile. All right, so I just did stream because I have a bunch of other stuff, but I can only run so many experiments. This was run on a small machine, whatever my desktop was. So the first one is an old study with an older desktop, and the right is a newer desktop. It's a top bin AMD gaming chip. And you can see here, and just to be clear, some of these numbers use one core and some use 16, but it's a 2-channel memory thing, so it saturates real quick. And then I threw the GPU numbers in there mostly to sort of troll the idea that there are some programming languages where you can just use the GPU trivially, and that's a really good performance feature. So the fact that you can just run C++ or NumPy effectively with CuPy on the GPU, you can't do that with Go, or you can't do that with some other things. So if you care about HPC, you probably this is more compelling than if you're Google doing data center work. So Google probably doesn't care at all that Go doesn't port to a GPU trivial, but it has proven to be interesting to see what you can get with some of the AI oriented languages like C++ and Python to just run something on a GPU. But overall, you see, you get about the bandwidth you'd expect in most cases. Ada, not so great. NumPy, problem there, you lose half the bandwidth because the way you have to write it runs over the array. It basically creates a temporary that doesn't belong. And if you use Numba, it goes away. So it's, some hazards to look out when you do complex expressions. NumPy may generate intermediates with it, which then chew up your bandwidth, and you need to think about how to work around those things. And then, if you see the left, don't write HPC code in Lua, Python not using NumPy, and don't do anything with Octave, essentially. Maybe MATLAB's better, but Octave you might as well use a pocket calculator. All right. Finally, I'm going to show GPU memory systems. I measure this stuff. And to be clear, obviously, where I work. So, don't count this as any sort of competitive marketing or any sort of serious number. Just go run the code yourself if you want. But what I've learned from this, with the different models, is you can see pretty easily the various characteristics. You can, you should be able to get the peak memory bandwidth with most models on most chips. But there are some interesting caveats. So one thing I saw was, at least in the past, and I think they probably will have fixed this by now, but at least 4 years ago or so, the Fortran compiler for the AMD GPU was AMD's Fortran compiler, not Cray's, to be clear, was noticeably slower than their C and C++ compiler. Who knows exactly why, but they've done a lot of work there and switched out the front end. So I think it's probably fixed. Obviously, use a Cray compiler. Cray's pretty good at Fortran, and they do a good job there, although you can still see a smaller number. I also got a one-tile Ponte Vecchio. This is not the Aurora SKU. This is the half-size SKU. So I've confirmed with Intel friends that these numbers are at least in the ballpark of correct. And again, there's a bit of a drop in Fortran, which again, if you're an HPC Fortran person, this is disappointing to see that Fortran, the language of performance gods, is in fact, inferior to C and C++ thanks to compiler issues. The other thing, of course, you could see is with the orange, with the unified memory, managed memory, whatever you want to call it, lacking page faults is obviously a bad thing. So you can see the very bad numbers are all due to something equivalent to the memory is on the host accessed via PCIe, and so it's as bad as you'd expect it to be. I found eventually, with some help from AMD, I was able to get XNAC working on the MI250X on Lumi, and got nice bandwidth. It seemed unreasonably painful, but I have actually talked to some folks and understood why XNAC is not on by default, because it actually changes code generation in DGEM, which you can imagine DGEM is kind of important for some other workloads on for AMD systems. So there's a hardware performance trade-off depending on whether or not you're using managed unified memory. On AMD, obviously NVIDIA stuff, that transition occurred in the Pascal generation, so you'll not see it anymore, but you would have if you went back in time. You'd obviously see probably some interesting and sad effects. And I've seen the Blackwell numbers, but they're not on the slide yet because I don't think I can talk about them. And if you have numbers on MI300 and you want to put them on the slide, feel free to share. So let's see. And lastly, this is the last thing I do. I mentioned earlier that one of the reasons I like the PRKs is when I get on a new machine that I don't know if I understand it yet, I run the PRKs, and I did some stuff with NW on GPUs, and one of the things that I was able to figure out pretty easily is that the porting strategy that I had to take was different than you would have thought about if you say, well, a quantum chemistry is just a bunch of big matrix multiplications. Well, it turns out big isn't sufficient to describe how big they need to be for you to do a dumb GPU port of NW-Chem. And so what you see here is the compute time on an H100, which obviously is pretty darn fast for DGEM, versus the transfer time with PCI Gen 5. And so, you look at this and you say, okay, well, I'm hitting 60 teraflops, give or take. But if my transfer time is, what is that, seven or eight times the compute time, well, then I'm going to get screwed. I'm not going to actually realize any interesting benefit. I don't remember what the teraflops is when you include the transfer time, but it's bad. And so, what I learned from this is, okay, you need to hide all the transfer time. And this is not a profound statement. We've known this for a long time, but you can actually put numbers on this and you say, well, actually, if your matrix dimensions are 20,000 by 20,000, yeah, you don't have to work very hard. Just do a simple port and run it on the GPU go burr, and you're done. And there are actually some quantum many-body calculations like GW theory for band structure, which have matrices that huge, and they can actually do a pretty straightforward port of their code. Whereas NW-Chem, because of how it's decomposed, ends up small enough that I had to do all sorts of crazy data flow stuff and make 50 asynchronous transactions in flight, etc. to get NW-Chem to run at 25% of peak, and I sort of tapped out there. So this is sort of use of for doing your application co-design. Start with something that's really simple, run a bunch of basic stuff, figure out the properties of your machine, and you can figure out with the PRKs where things land in terms of TLB, cache, bandwidth, peak compute, latencies, network behavior, etc., bisection, ping pong latency type things. And then you can think about how you'd go design software off of that. And then, of course, once you understand that those are all the patterns that matter, if you want to go design a chip, you can go think about using the PRKs in a simulator and saying, okay, this is something that I can actually run that I can't run some full app in the chip simulator in finite time. So there's some other stuff lately. I'm just starting now. Actually, last couple of days, Nickel and NV-SHMEM, or I haven't gotten there yet, but I'm getting there to write everything, take all the MPI code, port it all to Nickel, port it all to NV-SHMEM, and then see what's different. And then actually, my NVIDIA colleagues in research did CUDA STF, which is a sort of higher level programming model on top of CUDA, and they were able to get ported in. I think it took 2 or 3 days. I think we spent more time doing the the build system than we did the C++ code. Although I will say in my defense, the GNU make build system was simpler than the CMake business we were dealing with at the time. Anyways, so that's what we've been up to. The project is as active as I am. So, if you wanna play around and you see something interesting, let me know. I'm there on GitHub if you try something. And I won't really summarize because I've sort of said enough. And lastly, everything's on GitHub. Check it out if you wanna learn. I find I learn a lot about software. I take VimDiff and I just pull up two different implementations and I look at them and I say, well, do I like this one, or does this one look like it resembles math, or is it annoying? Anyways, so that's the end of the talk, and I thank everybody for showing up and look forward to questions.
I have a general question. Running any kind of benchmarking or doing any kind of benchmark activity, there's a multitude of ways to mess up, So you could misunderstand how a code is written. You could misunderstand the performance bottlenecks you should be up against and misinterpret the data in a big way. I know it's a problem you can't solve, okay? That's just the nature of benchmarking, that people misinterpret the data and draw conclusions that are not justified. But are there plans to give any, guidelines as to how to run these benchmarks? A simple example would be problem sizes, okay? We have a lot of stuff about problem sizes, and you can run tiny and small and big and extra large so that you're adapted to the architecture at hand. But I think you intentionally do not do that, right?
Yes. So Tim is retired from Intel, and Rob and I work for NVIDIA. So I no longer include a slide, but I will say when we were all at Intel, or any of us were into Intel, there was a slide that Intel Legal made us put that said, these are not benchmarks. And of course, this is strictly true because a benchmark has a much narrow problem space, right? LinPack has a single, there's a couple tunable parameters in LinPack, right? But LinPack is essentially you take a number, you run it, and it produces an output, and that really has some meaning, right? You've got a code, you say it's optimal, whatever. We agree on what it means to benchmark. The thing with the PRKs is there's too much flexibility to call them a benchmark, right? What I can tell you is if you run nstream and you fill memory until it's segfault, it's going to give you 99% of what McAlpin stream will give you, right? And that's true, right? If you take it down, it'll give you a different number. The DGEM number will also hit marketing numbers most of the time, right? But in general, we try to put these as, this is a tool. You can benchmark with it once you figure out how the tool works, but we're not publishing with the intent to make them benchmarks, right? And so in terms of caveats, so the thing we do try to do is eliminate nonsense by doing extensive validation. We also prescribe the decomposition, right? So with transpose, you can cheat by reblocking it, by basically changing the data distribution and making the network property different. And then you could claim, oh, I'm better, right? Because you cheated, right? So we do some stuff in there to say you can't change the code. We don't make it impossible, but we tell you don't change the distribution. You can't cheat this. But in the end, it is up to the user to pick a problem size that makes sense and to pick an iteration count that doesn't generate noise, right? So if some of these problems you need to run 1,000 iterations to get them to be smooth, because these modern chips have so much noise in them when they power on. So there's some stuff like that, but I haven't tried to curate this because nobody's asked me for it. And at least in the past, we've been afraid because if we do anything that makes them useful as a benchmark for people that aren't smart, then someone not smart will use them as a benchmark, publish them, and then somebody's legal department is going to get upset. Nowadays, I think, if somebody wanted to do something with it, I would say you can use this as a research benchmark, but I wouldn't tell anybody to do it for, commercial purposes.
Well, continuing on Georg's question, Jeff, would you say that the kernels are a good way of, let's say, testing of setting up MPI on a given architecture?
So, yes. And in fact, there's at least one PRK implementation that exists because some Intel colleagues said, I would like to make my machine as hot as possible. And so the multi GPU CUDA BLAS benchmark in there is actually set up. And so our first one is I wrote the MPI one, and then the person said, I don't want to install MPI. I just want to make my machine hot. And then I said, okay, so I wrote a version that didn't use MPI, but pumps the GPUs from one process, right? So if you want to think of them as smoke tests, they're great. Like what I can tell you is if you install the PRKs, you will break everything that's breakable immediately. So you will find out immediately if your compilers, obviously that's trivial. If your compilers don't work, you're dead. If you're OpenMP, you're going to find out your OpenMP runtime isn't any good. You'll find that out. You'll find out MPI is using TCP/IP sockets instead of whatever. You'll find that one out. You'll find out that your BLAS library you're linking against, which of course is configurable, but like if you compile against netlib or link against netlib, you're going to say, well, that sucks, right? You could find out a whole bunch of things. The other thing, and I will say they're useful for this, although I think a lot of things can serve that purpose. HPC Challenge used to do that. LinPack, even LinPack is great at that. What I have found, and this is the thing I'm very proud of, we have broken every software system ever, right? I think the only GCC compiler bug I've ever filed is or if I filed more than one, they're all from the PRKs. I've broken the Intel compiler more times than I could say. I broke the Cray compiler plenty of times. I broke the NVIDIA compiler. MPI, I can't say. I don't know. We definitely found some bugs in related to MPI. I got 100x improvement in Intel's CoArray Fortran, because we had the CoArray Fortran implementation, we ran it, and we said, well, this is 100 times worse than OpenMP and MPI, and there's no excuse for that. So then I called up the compiler team and I said, let's talk about what you're doing. And they went and they fixed everything. So we have made OpenMP better, OpenMP compilers. I mean, obviously a lot of this happened at Intel, so I can say we made a lot of Intel software products better. I've done a lot of work to improve the NVIDIA stack. So, if nothing else, like if you don't care about performance, but you just really like to break things, they tend to be pretty good at that too. I will also say, since, this is an academic group, I don't do academic education for a living, but Tim and I both, because we care a great deal about the topic, we actually think that this would be a great educational tool. Because if you're doing a class on HPC, you can't have people do anything complicated. And I think if I had to guess, Georg and Paula, when you teach it, at some point you probably do the heat equation with 2D, with MPI, right? And then you do some other stuff. And, you're going to do a bunch of things that an unexperienced person could do in less than a week. And I will say, that these meet that criteria. And the other part is, they're actually, when I took HPC, I told the professor, I said, I only know Fortran. And he was like, well, I don't. So you have to do your homework in C. And, the neat thing about this is you can actually have somebody we've got literally every language that is reasonable. And you can actually think about it as, well, do I want to teach you something new in a new language you haven't done before? Or if you're going to say, well, I only learned Java last year. Well, you could do it in Java. You might have to work a little harder for some cases, but I think there's some educational value here that hasn't been exploited because neither Tim nor I have ever had an academic position.
I have a question about the measurement infrastructure. So any of these kernels, they give you a performance number at the end, which means there's time measurement, and there's also decisions you have to make. How many iterations, for example, you do. And that has a direct influence on for example, statistical run-to-run variations that you perceive. And nowadays, that becomes, as you already mentioned, very important to report such variations. But to report a variation is not enough. You also have to report the conditions under which this variation emerged. So what kind of influence do I have here?
Okay, so this is one of my bits of shame or regrets is what we do in the PRKs. We always run a warm-up iteration. So if you say you want to do 10 iterations, it's going to run 11, and it's going to start the timer after the conclusion of the first one. And then it will run 10 real iterations with all of the memory touched and done everything the way it's got. All the network connections will be warmed on the first run through, and it will run and it will time 10 iterations, and it will then do divide by 10, and it computes all of the cost models analytically, right? There's no measurement. It's all arithmetic. My one regret or thing that I would fix if I had a lot of free time, which I don't, is I would completely redo all of the timing reporting to calculate min, max, and standard deviation, because we know that it's not just you warm up and then everything is peachy, although GPUs are pretty clean. Modern CPUs will, every bit once in a while, the daemon fires up, or if you're running on a network, obviously if you're on a contended network, you have to really think hard. I will also say, I have this, I don't think I've ever picked a fight with Torsten over this, but so I have a very strong belief that you want an was it L infinity? Whatever, basically the correct way to measure peak performance is with the minimum time, not the average time. Because this is not a computer is not a Gaussian system. A computer is a perfect system afflicted with all sorts of imperfections, and that the real number you want to understand the property of hardware, at least, is whatever the best you could possibly do and miss every divot. But of course, this is subjective. Some people out there will say, well, I don't care if my system could get fast one time if all the other times it's noisy. So I would love it, and I could, I just started using AI coding tools, so maybe I can figure out how to train the AI to go replace all this code, because every single PRK has the same stupid prologue, and it's all like I should replace it with a library version of this, and then just stick all the statistics, and then the user could say, this is the statistics I want. I just want the average because I don't care, versus I want a histogram, and then you could, I could pump all that out. But NVIDIA is not paying me to do that, and it's not my hobby. So if you want to write a paper, I would be glad to do the work. But other than that, I don't know when it'll happen.
There's one problem if you really put in statistics in a consistent way, and this is actually want to go down to the single measurement. So one run, one sweep of the Stencil kernel, whatever. But depending on the problem size, that could be a very short time that you cannot even measure properly with the standard timers that we have. Like it's on the order of microseconds. And then even if you do statistics on that, the whole values may be off. But that's a problem that you cannot go down to arbitrarily small problems if you really want to do consistent statistics. So it's a difficult problem.
Yeah. The good news, at least, is I've abstracted away the timer, such that if you don't like STD chrono or OMPW time or MPIW time, you can put in your read MSR counter and get that. But you're right. No, what I would like to do is capture a vector of times and then be able to have user configurable statistics on that. I think it's the right thing to do at this point.
Okay, are there any questions from the audience still? Last chance. Okay, final question from me. Why do Americans hate Fortran more than Europeans?
It's what's his name? What's the Dutch guy? Edsger Dijkstra. Dijkstra has all these, rants about it's bad programming. It's not a rant about Fortran, but I think I've seen quotes, the equivalent, the polite version of Fortran is a brain disease, all this stuff. And this has been sort of adopted as a meme because, Dijkstra is a computer science god. And so you hear basically all these computer science professors in the US maligning Fortran. And I think part of it is the lack of collaboration between the industry where Fortran is used and the computer science sector, which in the US, as you know, right, computer science, if you go to Stanford, right, every Stanford CS major wants to go up and invent a new Google. None of them want to go out there and, simulate the front end of a Mercedes or an Airbus 300. Whereas, I know, at least some of the, for example, some of the German HPC centers have Porsche or so-and-so as a customer, and that interaction with academia and industry and national labs that's actually demonstrating that there is a real purpose for Fortran. I think I don't really hear Europeans making fun of Fortran. They actually say, no, well, we like it. It actually works well, and we learned to update our code to Fortran 90 at least. But that's as best I guess I want to blame Dijkstra for most of it, but it's there's certainly some differences that I've observed.